Alright, so we left off at detailing the high demand for the synthesis of tixobactin and why we should go ahead and synthesize tixobactin. But I'm going ahead and go to and describe the actual synthesis of tixobactin. So tixobactin is a synthesis of tixobactin analog is completed using solid phase peptide synthesis. And in this particular study, 2-chlorotrityl chloride resin is used here in his structure. You have 3 phenyl rings. 1 chloride is attached to one of the phenyl rings, and you have this very good leaving group chloride here that is very prone to nucleophilic attack, or the carbon that gets attached to is very prone to nucleophilic attack. So usually what happens when you attach the amino acid to this resin is the carboxylic end attacks this carbon here, and this chloride leaves. And what happens, usually these amino acids that are attached or that are used in solid phase peptide synthesis have to have the N-terminus or the amino end of the amino acids protected, and it's usually done by FMOC or BOC. And this is the structure of FMOC here. FMOC just stands for fluoroanyl-methyloxycarbonyl chloride. So the first amino acid that is used to attached to the resin is FMOC L-alanine. And like I said, the carboxylic end is what attaches to the resin here. So whenever you see FMOC is attached to the amine end of the amino acid, and the attachment of FMOC L-alanine is done in DIEA, or N,N-diisopropylethylamine, and that's a very hindered base, and it has to be hindered. Well, the base is used to it's used to deprotonate the carboxylic end of the amino acid so that it becomes more nucleophilic, and it actually attacks the tertiary benzoic carbon that chloride is attached to. And it's usually done in dichloromethane. It has to be hindered because it has the potential to remove this very acidic hydrogen in that FMOC group, and if it's hindered, it won't react with that hydrogen there. So that's a requirement. And from here, we need to attach other amino acids, and it's done by deprotecting the FMOC group using 20% piperidine and dimethylformamide. So after the deprotection of the FMOC group, the amino acid that is being added is dissolved in HATU and N,N-diisopropylethylamine, and is then added to the resin. And this is repeated until the tetrapeptide formation right here. And so just to clearly describe this procedure here, we remove the FMOC group using piperidine. So the next amino acid is D-threonine. So we remove this FMOC group, we free the amine group, and what we're doing, we're making amide bonds, right? Because the carboxylic end of the D-threonine will react with the amine end of the L-alanine. But in order to have the amine group of the L-alanine, it needs to be freed up by the FMOC group. And so D-threonine is dissolved in HATU and DIA. After the FMOC is removed, we add the mixture to the resin, and we shake it, and there we go. We have the amino acids coupled. And after the addition of D-threonine, you'll see that the amino end of D-threonine will have FMOC attached. It's not showing it here because it's just showing that the same procedure is being repeated until you have this tetrapeptide. So every amino acid undergoes this procedure here, or these 4 amino acids undergo this procedure here, and it doesn't change until the ester formation of the D-threonine residue and the L-isoleucine residue is formed. So this takes place with the D-threonine hydroxyl group reacts with the L-isoleucine carboxyl group, and this is done using DIC or N,N-diisopropyl carbodiamide, and 4-dimethylaminopyridine, or DMAP, and DMF. And after that step, we have a removal of the alloc group, and then alloc arginine is added to or coupled with L-isoleucine, and it's done just as the previous amino acids were added to the deprotected amino acids from or after the deprotection of the FMOC group of the previous amino acids. The alloc arginine is dissolved in HATU and DIA and DMF, and the attachment is done that way because that would be the only amino group that is free to react with the arginine, or the arginine's carboxyl group. And so at this point we have the FMOC group that is still attached to the L-isoleucine here at the end of the molecule, and we have the L-arginine that was just added to the amino end of the L-isoleucine. So the rest of the amino acids after L-isoleucine are added just as previously mentioned. We deprotect the FMOC group, mix the amino acids with HATU and DIA and DMF, and all the way until you have this peptide form. So you have FMOC-D-allo-isoleucine added, FMOC-D-glutamine, FMOC-L-serine, O2-butoxide, I'm not sure how to pronounce that, to be honest. And you have this odd N-methylphenylalanine attached as well. And in order to create the cyclic structure here in the peptide, we need to go ahead and remove the alloc group of the arginine, and after the removal of the alloc group, the resin or the peptide needs to be detached from the resin, and that's done using trifluoroacetic acid, or tetrafluoroacetic acid. No, it's trifluoroacetic acid, sorry, and DCM, and that just completely removes the resin, or just detaches the peptide from the resin. And this glycylation and deprotection is done using DIA, oxymopurine mixed in DCM and DMF. It's then cooled in an ice bath, and PYAOP is added, and that results in the yield of this teixobactam analog of being 6%.